good to go, I think. Alright. Alright, welcome to the first stream in the OpenGL series. If you're wondering why I'm doing this, episode 7, I'm just going to redo, I think the first 10 streams because the music made it unhearable, so I'll just redo that since I learned how to actually fix the music. So 7 through 18, those streams will be redone. So we're just going to start off from the beginning, I guess, with displaying shapes. So in episode 6, we simply displayed a window. We have a color in there, or no, I don't know if it was episode 6, but as of now we have a window displayed. We've looked at GLM, how to use that, and we have all the libraries installed as of now. So today we're going to be looking at the graphics pipeline, just a very brief intro into what the graphics pipeline is, and then we'll look at how to pass data into it and how the pipeline actually interprets data and puts colors on the screen that you can see in the window. So in general, the function of the graphics pipeline is to take 3D coordinates that we give it. So the coordinates that we give it are going to be in 3D space. It's a 3D graphics language or library, OpenGL is. And then it's going to convert that into 2D coordinates since the screen is only 2D. If we were in a virtual reality thing, or you know what, virtual reality is still 2D technically, but if we were in the future and we had like holograms, then you would be able to cut out that 2D or 3D to 2D conversion. But as of now, we have to make do. So what it does, so the way that it does it, is it takes in a bunch of data. So let me just tablet. So the program takes in a bunch of data in 3D, and then it just passes it through a shader program. So, and we have to write the shader program, and then I believe it's still in 3D after this, and then or is it? I might be, yes it is, okay. So yeah, it's still in 3D after the shader, and then it goes through some things in OpenGL, and then it goes to 2D for the screen. So our shader, its purpose is just to kind of modify the data or interpret the data and pass it in a format that OpenGL can then read and make into 2D properly. So essentially what we give it is a bunch of different fragments. So we have as many fragments as we need in our models. So when we get to object files, they will just be containing a bunch of different fragments. And each fragment has vertex data, so position, and we'll add some attributes later on, but as of now it will only be position. And then it goes through the shader, give it a normalized position. We'll learn what that means, and then it'll pass through a couple other things and get to a 2D representation. So let's start off by we'll look at the shaders right now, and then we'll look at how to pass data into it. So in the folder, OpenGL tutorial source. Do we not have assets yet? Oh, we don't have that folder yet. Okay. So I'm going to create a new folder called assets, and in assets I will create 2 files. So touch. Let's say. So the first one's going to be the vertex shader. So We'll learn what all this means. So vertex underscore core.glsl. So the shaders are written in a language called GLSL, Graphics Language Shader Language. I think, wait, no, I forget what it stands for. But it's like a simplified C. It looks a lot like C. And it's run on the GPU or whatever graphics card you have. And the thing is, these programs are all very small. So we have a bunch of different shader programs, and they all run parallel to each other to generate the screen. So then we also want a fragment core. So touch fragment underscore core.glsl. So this is the fragment shader. So the vertex shader will take in we'll pass in the data to the vertex shader. It gets run first. It sets the position that we want it, and then to be passed into OpenGL, and then we output it in, and that output is in normalized device coordinates. Once again, we'll look at what that means. And the fragment shader essentially requires an output of a 4D vector, which will be the color. So let me just refresh here, include all of this stuff here, and let's look at the vertex shader first. So standard for all of your shaders, you have to have a macro stating what version it is. So what version of OpenGL? So we're going to say version 330 core. That's just what we're using right now. Then we're going to say this: layout location is equal to 0 in vec3 a pose. So what this means is layout is just saying in the data that's passed in, we're going to go to the 0th index of the data and take in a 3D vector and call it a pose. Then in the main method, we're going to say void main, because remember, these are all different programs. There's a shader program that runs every frame. Then we're just going to say gl underscore position, which is a predefined global variable that must be assigned a value, is equal to vec4. Then this is a constructor, so we're just going to say apose.x, or you can just say apose and then 1.0. So GLSL is super versatile in that you can pass in, at least with the vectors, you can like do a bunch of weird shit with this. So if this was a 2D vector, I could say 1.0 and then just say .yz, and this would still be valid. There's a lot it's super helpful in a lot of different ways, but for now, we're just gonna, this looks pretty simple. So what it does is it just takes the 3 values from the 3D vector and then puts it with a 1 and makes that a 4D vector, which will be the GL position, which is then passed in OpenGL and given and then projected onto a 2D plane. Okay. Yep, so that's the vertex shader. Now for the fragment shader, we're gonna have the same macro at the top. So hashtag version 330 core. Then remember, we have to output a color. Now with the fragment shader, there isn't a predefined variable, so we have to make it by just saying out vec4 frag color. So what this says is we're going to output a 4D vector called frag color, and because it's coming from the fragment shader, OpenGL knows automatically that this will be the color of the fragment. Then we say void main, same thing, it's another program, and then in here we can give it any color. We're just going to say frag color is equal to vec4. Now note that this is in normalized values, so 0 to 1 instead of 0 to 255 for RGB. So 1.0 float, so that would be equivalent to 255, then 0.2 float, and then 0.6 float, and then 1.0 float. This 1.0 is the alpha value. We'll just keep it at 1 for now. It wouldn't matter either way, but yeah. Oh, I didn't explain this, but in the vertex shader we have this 1.0 here, just because this is going to be very important when we get to more advanced lighting and shading. And it just also helps with transformations too, because we need a 4D vector to multiplied with a 3D transformation matrix. Okay, so yeah, this is all we need for the shaders right now. Now we're going to get a way to compile them in OpenGL. So in main.cpp, we can delete the GLM test. Doesn't really matter right now. And then we want to include a couple things. So we'll first include fstream, include sstream, include stream buff, include string. And then we're going to create a callback to a method. So standard string, it returns, and then we're going to say load shader src, and we're going to pass in a const char star file name. So this function will be used to actually load the shader source, because remember, these files, we have to tell it which source code to actually look at in the shaders. So we'll implement this, let's just do it right now actually, just to get it out of the way. So I'm going to implement it at the bottom underneath the process input method. So same signature, so standard string, load shader source, const char star file name. So we're first going to create our file, or create the file object. So standard ifstream file, standard string stream buff. This will be the buffer to read the data into. Then we're going to say standard string ret is equal to an empty string. So this will just be our placeholder for the return variable. Then we want to open the file. So file.open, pass in file name. Then if file.is_open, just to make sure that the file is open, we're going to read the file into the buffer. So buff, then two less than signs, file.rdbuff. So this is the read buffer, and we're just essentially piping it to the string buffer, the string stream that we have up there. Then all we have to say is ret is equal to buff.str. And then otherwise, we just want to print out an error message. So standard cout could not open file name std endl. And then to close the file, so file.close, and then return ret. Just like that. So this method will we'll pass in a file name, and then we'll read the file, and then we'll compile it. So now how do we compile it? Because it's not going to be, this file isn't going to be run by the C++ compiler. We have to compile it during runtime. So this shader here, we have to compile both the vertex and fragment shaders as we're running the program. So let's go back into main.cpp, and underneath where we set the frame buffer callback, we're going to start the shaders. So we're going to compile the vertex shader first. So in OpenGL, what you're going to see is that a lot of things are represented using unsigned integers, and these are locations in memory on the graphics card. So we're going to see shader programs are represented using integers. Memory vertex data is represented, or at least we represent it on our side using integers, which we will then bind, which means we'll bind a specific location in memory to be the active vertex, or the active shader program. We'll see how that works. So we're going to say unsigned int vertex shader. So this will just be the vertex shader object. Then we're going to create a shader. So vertex shader is equal to gl create shader. And then we have to pass in a type. So gl underscore vertex underscore shader. And then we want to get the source. So standard string vert shader src is equal to load shader source. And then we're going to pass in a file name relative to the root of the solution, because that's just how Visual Studio does it. So it's going to copy all the, well, not really copy, but it's going to run the executable. So our OpenGL tutorial.exe, it's going to run that and essentially putting it in the project directory. So assets will be in the same so the assets directory will be in the same level as the executable. So we say assets / vertex _ core.glsl. Then we want to say const gl char pointer vert shader is equal to vert shader src.cstring. So we're just getting the vertex shader source as a string, and then we convert it to a const char star, which is then automatically casted to a type of GL char. Now we're gonna set the source in the shader object. So GL shader source vertex shader, so the current program or the current shader, 1 for the count, then the string of data, so a reference to vert shader, and then the length we can just say is null. Doesn't matter right now. And then we want to compile it, so GL compile shader vertex shader. Then we want to catch an error if an error happens. So we first have to have some placeholders up top to actually determine if this error was generated. So at the top, we're just going to have an int success for the success code of the compilation, and then a char info log array of length 512, just to store the message if there is one. So for the catch error, we're going to say this. So GL get shader iv vertex shader GL _ compile _ status, and then a reference to success. So this is telling OpenGL, or the code, to get the shader value, and we want to get the GL compile status. Then if not success, so success was not equal to 0, so therefore there was an error, we have to get the info log. So GL get shader info log vertex shader length is, or the buffer size is 512, null for the length again, and then the info log will be info log. Then we can just print out standard cout error with vertex shader comp, and then we can print out the info log. Just like that. So we can determine we can determine if there are errors runtime, or during the runtime. Then we're going to do practically the same exact thing for the fragment shader. So compile fragment shader. So unsigned int fragment shader. Fragment shader is equal to GL create shader. This time the type is GL fragment shader. Then we're going to get the source again. So standard string frag shader source is equal to load shader source, and the path is assets / fragment _ core.glsl. Then const char star, or const gl char star, frag shader is equal to frag shader source dot c string, automatically casted to a gl char, and then we just say gl shader source fragment shader 1 reference to fragment shader, null for the length again, then compile. So gl compile shader fragment shader. Okay, I mistyped. It's the in GL shader source. The third argument should be a reference to frag shader, not fragment shader, because we want to pass in a reference to the actual shader source. Then we're going to get the errors again, so you can actually just copy and paste the catch error. Just make sure to change the names. So GL get shader IV for fragment shader, GL get shader info log for fragment shader, and then error with frag shader compilation. Okay, now we're going to link these two shaders. So we have them, but it would be kind of annoying to bind both of them separately. So what we do is we create a shader program to link the two. So when OpenGL looks for a shader, it looks for a shader program. It then passes the vertex and the data to the vertex shader, and then goes to the fragment shader. So it wants to know which fragment shader is paired with which vertex shader. So we have to link them. So we're going to have here unsigned int shader program. Same thing again. Then shader program is equal to GL create program. This is very similar to what we've seen. Then we want to attach the shader. So GL attach shader, shader program, and vertex shader. Then GL attach shader, shader program, and then the fragment shader. And then GL link program to link them, shader program. And then we want to get the status again. So we're going to catch errors again, pretty similar. So GL get program IV this time. Shader program, GL underscore link underscore status, and then a reference to success. Then if not success, GL get program info log, shader program. The buffer size is 512. The length is null, and info log is the output of the errors. Then we just want to print it out again. So as standard cout linking error, and just print out the error log as before. Okay, and then we want to clean some shit up. So we can actually delete the vertex and the fragment shader now because we have linked them, so we don't need them anymore. So GL delete shader, vertex shader, and GL delete shader, fragment shader, just like that. But we are not done yet, or that's the first half of what I wanted to do right now. We're now getting into the second part. So we have compiled, generated, and linked our shaders into a program. But now we have to set up the actual data to pass in. So let's look at how we're going to do this. So in OpenGL, so what I'll do first is I'll draw out kind of what how the memory looks, and then we will write the code. So the same way that you have a shader program that links a vertex shader and a fragment shader, we're going to have a kind of a container for pointers to data buffers. So what this one's going to be called is a vertex array object. or VAO for short. And this is going to be a wrapper for the vertex data that we will pass into the graphics card. So it's essentially going to contain pointers to the data buffers. So our VAO will essentially look like this. There's a box. Well, there's not a literal box, but you get the gist. And then in this VAO, we're going to have pointers to some data, other data, other data. And this data is going to be stored in the most part in a vertex buffer object. Or a VBO. And what the VBO does is it's essentially a vertex buffer object. We give it certain data. So let's say that this is X, or let's say we had our first vertex, so V at 0, V at 1, and so on and so forth for n vertices. We're going to have an array of vertices, of vertex data here, so an array of positions, which we can represent just using floats. It doesn't really matter right now. And then we'll essentially tell OpenGL that this VAO here should point to this VBO. And then when we draw an object, we are going to bind this VAO here, and it will know what VBO data to look for. So yeah, let's say this was location 0 or VAO 0. When we bind the unsigned integer 0, the graphics card knows that this is the current VAO right here that we want, and then it knows what vertex data to look for. And then we'll pass that data into the shader program, which will do how many of our operations you want. So that's how kind of how the graphics card works in tandem with the data here. So let's just actually go ahead and hop right into it. So we're going to have our VAO and VBO first. So unsigned int VAO and VBO. Then we're going to say GL gen vertex arrays 1 and then a reference to VAO. Then for buffers, we're going to say GL gen buffers 1 and then a reference to VBO. We'll start with the VAO. So to actually tell OpenGL which vertex buffers belong to which array objects, we just have to have the VAOs bound while we're doing stuff with the VBO. So bind the VAO. So GL bind vertex array VAO. So this just passes in an integer, and the graphics or OpenGL will know which vertex array object is the active one. Now we want to do the same thing for the VBO. So bind the VBO now. So GL bind buffer. The type is going to be GL array buffer, and then VBO. Then we're going to set the data here. So GL buffer data, GL underscore array underscore buffer. Then the size will be size of vertices, which we haven't, I didn't even create that, I'm sorry. So we'll create this array in half a second. Oh, my computer just went to sleep. Sorry, 1 second, okay, yeah. Vertices, and the vertices array we'll put in there, and then usage will be GL static draw. So you can kind of infer what static draw means. It just tells OpenGL that we won't be modifying this data much. So it will put it in a location that's convenient. There's two other possibilities. There is GL dynamic draw, which means that we will likely be changing this every frame. So it will locate the data in a easily accessible spot. So now for the vertex data, we're going to have our vertex array up here. So we'll start with a triangle. So float vertices, and this will be a float array. And so these coordinates have to be normalized device coordinates. That means -1 to 1, where, let me just draw this out quickly. So normalized device coordinates, NDC for short, not the DNC, the NDC. So let's say our screen is like this, and this is our kind of principal axis, or I'll draw the screen and then I'll draw the axes in it. So normalized device coordinates means that the bottom left is -1, -1, and thank God it's the bottom left, and the top right is 1, 1. So we essentially have two axes here, the Y, the X, and the Z, which we will get into in the future. Just like that. Okay, so if we just want to have a simple triangle, we can say minus 0.5f, minus 0.5f, and then we have to have the z coordinate. So we can just say 0.0f for that for now. Then we'll say for the top point, 0.0f in the x direction, 0.5f in the y direction, and 0.0f in the z direction. Then for the bottom right, we'll say 0.5f, -0.5f, and 0.0f. So this will be the vertex data. But as of now, to OpenGL, this is just bytes. It doesn't know what it is. It just knows that it's some data. Like, it knows how much data, it knows what data to look at, but it just sees this as bytes. So let's look at what this would be in memory. So since this is an array, we just have a string of data here. And it was 9 boxes, I believe. So we had -0.5, -0.5, 0.0, 0.0, 0.5, 0.0, and then 0.5 minus 0.5 and 0.0. So this is, it doesn't even know that this data is -0.5 because we haven't told it that yet. So what we have to create are vertex attributes, and this tells OpenGL how to interpret this data. So it knows, what OpenGL knows right now is where the data starts, so it knows this, and it knows how much data there is, because that's what we pass in GL buffer data. So it knows that. Now we need to tell it what to do with the data. So we're going to have a couple of things here. So in a vertex attribute pointer, we're going to have an index. So in what you will see is, as the series progresses, we will have multiple attribute pointers, or multiple attributes for the vertices. There will be a color, there will be normal vectors, so on and so forth, and it needs to know what indices there are. So since we can have multiple, we're going to have different indices. So for now, we'll just have 0. Next is the number of values per vertex. So for us, since we have a 3D vector, we want it to read every 3 values as one vertex. So this is the number of values, which is 3. Then it wants to know what type of data it is. So we're going to give it an OpenGL macro, so GL underscore float. And this will tell it the size of each element in the array. So it knows now the size of here, which is 4 bytes. So therefore it knows that each vertex is a total of 12 bytes now. So this is equal to the number of values. And this is equal to the size of the type. I miswrote. And then the 12 bytes is equal to the number of values times the size, or the size. Now the next thing we wanted to do is have a stride. So here, what we're going to say is this stride is going to be the distance from the start of one vertex to the start of the next vertex. So for us, it's gonna, for right now at least, it's gonna be the size of it. So stride, and here it's just gonna be 3 times the size of the float. I keep miswriting. So this is also gonna be equal to the stride. You might be wondering, well, why do we need this if it's going to be the next one? Well, when we start interlacing more data, the next vertex might start a little further along if we have other data embedded in the vertex. There are different ways to do that, and then we also have an offset, which for now will equal 0. So that's kind of what the vertex attribute pointers will do. So now, what it does is in the vertex shader, it knows location equals 0. That's the index. It takes in a 3D vector. So OpenGL knows, give it 3 floats in an array. So, and then the shader will interpret that as a 3D vector and pass it in to the vertex shader. So, oh God, my computer keeps wanting to sleep, or my reference. So let's actually go ahead and write this. I need to turn sleep off then. Hold on. All right. Should be good now. So let's set this pointer. Alright, so GL vertex attrib pointer. The index is 0, size is 3, type is GL underscore float, normalized is equal to GL false. Don't worry about that right now. We don't care about it. Stride is going to be in bytes, so 3 times size of float. And then the pointer for the offset will be a void pointer 0. So 0 cast to a void pointer. Don't worry about, or that just, it's weird syntax, but, or it's weird that we're doing this at all, but that's just what it wants. And then we have to enable it. So GL enable vertex attrib array 0 for the index. Alright, so now we should be good to draw. So in the main loop, we're going to go ahead and draw some shapes. This is exciting. The climax is coming. So we're first gonna say GL bind vertex array VAO. So now OpenGL knows which vertex array object to look at, and as a result it knows which vertex buffer data to look at. Then we want to use the shader. So GL use program, shader program, because it needs to know which shader program to actually pass the data into. Then we want to draw the data. So GL draw arrays. The type or the mode is GL triangles. First is 0 and then count is 3. So the first will be the first index to draw at and the number of vertices to draw. You guys ready? If this fucks up, I swear to God. Oh yeah, attaboy. You'll love to see it. So that's a nice triangle right there. And what you'll notice is that if we resize this, the coordinates are normalized. So they will resize with the window. They will stay at negative 0.5, negative 0.5 in the normalized direction. So hell of a job. Nice. So let's do something a little interesting here. Let's try creating a rectangle. So there is, you can read more into this, but we can't just give it 4 vertices. Right now at least, because OpenGL only knows how to draw triangles, and the reason for that is, well, graphics cards only know how to draw triangles because it's super efficient because all 3 points are on the same plane. So there's a lot it can do since it's on the same plane. And that I mean in terms of shading of colors, because you saw how when we ran this, it didn't just draw the points, it drew everything in between the points. It filled everything in. What you'll see in a bit, when do I do this actually? In a bit is that you can actually specify colors in the VBO, and it will interpolate the color. So yeah, we can actually, let's actually look at that right now. So I'll pass in I'm going to do something weird here. So in the vertex shader, I'm going to output a fragment color. So out vec4 frag color, or color. And then in the fragment shader, I will take in a color. So you can pass data between the vertex shader and the fragment shader. So the fragment shader will take in vec3, or yeah, vec4 color, same name. And then I'll just say frag color in the fragment shader is equal to color. And then I want to change this, so let's say here, so if apose.x, you can get the x component, is less than 0.0, let's set the color to is equal to vec4, let's make it a green, so 1.0, 0.0, 0.0, and 1.0, or that's red. Else, if apose.x is equal to 0, we're going to say color is equal to vec4, 0.0, 1.0, 0.0, and 0.0, and 1.0. And then else if, or else rather, it's going to be greater than, so we'll just say color is equal to vec4, the blue. So 0.0, 0.0, then 1, 1. Just like that. And just to demonstrate once again how versatile vectors are, we can say this, vec4, or color is equal to vec4 of a vec2 of 0.0 to set all the values to 0, and another vec2 to set all the values to 1.0. Okay. So if we run this, so you see how the colors are interpolated. And once again, it is able to do this pretty easily because all the points are on the same plane. We don't tell it which point to look at in the center. We don't tell it every single color value to shade. It just interpolates the colors, which is actually pretty cool. But yeah. So yeah, that's some cool stuff there. Yeah, so we can actually just remove this because, yeah, let's remove this for now. Or, yeah. That's just a cool exercise, though. And then for the fragment shader, just revert it back to the original. What's up, Ezekiel? So back into main.cpp, let's go ahead and create our rectangle. So once again, 2 triangles. So we'll have the first triangle. So let's have the upper right, so 0.5f, 0.5f, and 0.0f. So top right. Sorry, let me just check something really quick. Alright, we're good. Then the top left, so negative 0.5f, 0.5f, and 0.0f. Then the bottom left, so negative 0.5f, negative 0.5f, and 0.0f. So bottom left. Then for the second triangle, we're going to say the bottom left, so 0.5, negative 0.5f, negative 0.5, and 0.0. And the bottom right, so 0.5, negative 0.5, and 0.0. And then the top right again, so 0.5, 0.5, and 0.0. So now if we told it to draw this, we would just have to tell it to draw 6 vertices now. So in GL draw arrays, it becomes GL triangles 0 and then 6. So if we run this, we should get a nice rectangle. And I believe there is a way to draw only lines. Let me actually just experiment with this real quick. So GL lines. This might not work. Yeah, so okay, that didn't work as I wanted it to. I forget how to do that, but there is a way to show that it's actually just a wireframe. Triangle strip. That might work. I'm just experimenting. Fuck, no, okay. Alright, so just GL triangles for now. So you might notice here that this is pretty inefficient, right? Because you're repeating the top right and the bottom left twice. So what if there was and you can imagine that once we get into more complex objects, that since a lot of these objects are going to be closed objects, so they'll have like a solid body, so many of these vertices will be shared. So you're definitely going to see how this can become super inefficient and super memory consuming very quickly. So this introduces the concept of another type of buffer. It's going to be called the element buffer object, and this will store the indices of vertices to draw. So it's going to be 2 separate things. So the vertices will have its own array, and then we'll have another array of indices. So in memory, I'll just draw this out again. So let's say we had our vertex, our first vertex, then our second vertex, and then the 0th. I meant to put that up top, or in front. So this is the top left, so, or top right, top left, bottom left, and then bottom right. And this is the rectangle that it produces. So TR, TL, BL, and BR. So 2 triangles, and if we have an element buffer object, we can pass in indices of triangles. So we'll say 0 for the first triangle, 0, 1, 2. So that tells us do the top right, the top left, and the bottom left. And then in the second triangle, do the bottom left, so 2, 3, and 0. So bottom left, bottom right, and then the top right, and then it'll complete the triangle. So yeah, so we're gonna essentially create an integer array here and set it up as another buffer and bind it with the VAO as well. So this is just another buffer that the VAO will point to. So it'll be another one of these pointers here that the VAO will associate with the data. So now in the vertex array, we can get rid of the duplicate vertices. And now we can have our integer array. So unsigned int indices. So this is equal to, I said 0, 1, 2, then 2, 3, 0. Yeah. So 0, 1, 2, and 2, 3, 0. So this is the first triangle, and then the second triangle. Doesn't, okay. So we're gonna bind it pretty much the same way, or generate it the same way. So, we're gonna have it's gonna be represented with another unsigned integer. So EBO. Then we just want to say GL gen buffers again, 1, and then a reference to EBO. Then down below we want to set up EBO. So GL bind buffer. This time the type is going to be GL element array buffer. So this is how OpenGL knows what type of buffer it is this time. And EBO for the buffer. Then the data will be GL buffer data, GL element array buffer. The size will be size of indices. The data will be indices, and then usage will be GL static draw again. And we don't need to set up any vertex attribute pointers because it's an element array buffer, not a vertex array buffer, or a vertex buffer object. And we don't need to do anything else special because the vertex array is already bound properly. So yeah, this since the VAO is currently active, whatever we do right now in terms of buffers will be passed into this. So yeah. So now in the main loop, it's just going to change the draw command will change, so it'll be GL draw elements, GL triangles. The count will be 3 for 6 indices. Then the type will be GL unsigned int for the type of index, and then indices will be 0 for the offset. Yeah, so now let's run this and we should get the same results. There we go, same thing. Nice. So let's do a little more experimentation. Let's try creating another fragment shader that has a different color set, just to show you how the triangles are actually drawn differently. So I will go ahead and create a new file here. I'll call it fragmentcore2.glsl. You know, let me actually just refill my water real quick before I get into this. So in this new shader, let's just copy the code and just change the color slightly. Yeah, so let's make this a quick 0.5, 0.82, and then 0.11. Don't know what color that is. Now in main.cpp, we essentially have to do the same thing, but we will, we're going to compile another shader, essentially. So this entails creating another shader program altogether. So up where we create our shader, our fragment shaders, I'm going to create an array of fragment shaders. We'll have an array of fragment shaders and then an array of shader programs as well. So this is going to be annoying to change the name. So fragment shaders becomes now an array of size 2. And so change all the code with the fragment shader right now and make it fragment shaders at 0. Now we have to do the same thing with the shader programs. So shader programs is an array of size 2. Then shader programs at 0 now becomes, now is what we should be doing the operations on. So just change all the names, and then we can also just run this just to make sure everything works still. Alright, so let's run this just to make sure everything's good. Yep. Alright. So let's start by compiling the second fragment shader. So just copy the code actually, and just change the numbers or the index to 1, and make sure that the file name is assets/fragmentcore1 or 2.glsl. Alright, now for the shader programs, do the same thing. Just copy and paste the program generation. And change the indices to 1. That's the indices of the shader programs and the fragment shaders. If you are confused, all this code is on the GitHub if you want to this code is going to be outdated, or the commit's going to be buried deep, but it's just called episode it just goes with the episode that we're on, so episode 7. And then we just want to GL delete shader fragment shaders at 1. And we don't need to create a second vertex shader because I don't want to change that. I just want to keep it the same. So yeah. Now for the drawing, it's going to be a little different now. So we will draw the first triangle using the first shader, and then the second triangle using the second shader. So GL use program shader programs at 1. But now we have to change a couple things here. So the first call to GL draw elements, we want it to draw 3 vertices only. So change that 6 to a 3, and then we can kind of duplicate the call, except we have to change the offset. So underneath where we use the first or the second shader program, change the offset to we're going to say the offset has to be 3 indices, right? So it's going to be 3 times size of unsigned int, and then we just have to cast it to a void pointer, just because it's an offset once again. So now when we run this, we should get the 2. Oh, there were build errors. I just forgot a parentheses. Yeah, parenthesis. Oh, okay. And then also when you're copying and pasting, make sure that you don't redeclare the type of fragment shader source in frag shader. And it doesn't matter. You don't have to create new variables because we've already passed in the data to the shader program. So you don't need to do anything separate. So now if we run this, we should get the 2 triangles and they have a different color. I'm sorry if you have color blindness, but you know what? You should not have been so weak. So yeah, I'll say a couple more things here. With the element buffer object, there was this is also helpful because if we're drawing multiple things, you could use 2 different vertex buffer objects. But let's also try and create something here. Let's create a little bit of a figure, or no, sorry, that's wrong. I'm just going to change it so that we'll draw side-by-side triangles just to show you how it doesn't only apply when it has common vertices. So I will create this again. So float vertices, and for the first triangle, we'll have negative 0.5, negative 0.5 and 0.0. Then we'll have negative 0.25, 0.5 and 0.0. Then for the final, in our vertex, we'll say negative 0.1, negative 0.5, and 0.0. And then for the second triangle, we'll have, I'll say 0.5, negative 0.5, 0.0, 0.25, 0.5, and 0.0, and then 0.1, negative 0.5, and 0.0. And then for the indices, this defeats the purpose of a element buffer object, but it's just going to be 0, 1, 2, 3, 4, 5. Because there's no commonalities right now. So 0, 1, 2, 2, 3, 0. So you could actually just use GL draw arrays right here and it wouldn't change anything. Oh, did I screw something up? Oh, I typed in something there, but why is it not drawing the second one? Oh, because I didn't change the indices. So it's 0, 1, 2, then 3, 4, 5. There we go. So you have two triangles on the screen. You can do whatever you want with them. You can make a dildo. Maybe I'll make a 3D model for a dildo soon. I actually don't think that YouTube would like that, but yeah. So this is a good place to stop, I'd say. Oh, one thing I forgot. And then I'll say one more thing after this. We just forgot to delete the buffer arrays, the vertex arrays, once the loop is over. So GL delete vertex arrays 1 and then a reference to VAO. GL delete buffers 1 and then a reference to VAO. And then GL delete buffers 1 and then a reference to EBO. It just cleans out the memory once we're done. So yeah, that's pretty cool stuff. So final thing I want to say is with the VAO, we can have the same VBO binded to multiple different VAOs. The only thing that matters is that you have to reset the vertex attribute pointers both times. So if we wanted to interpret the data differently for two different VAOs, you could do that using the same VBO. So the VBO doesn't have to be generated when the VAO is bound. It just has to be that the vertex attribute arrays are set when the VAO is bound. So yeah, that is a good place to stop, I'd say. Good, very nice two triangles there. You can do whatever you want with them. Like I said, make a dildo, send it to me. And then yeah, so this is a good intro, and next time I believe we're gonna be going more into shaders, I believe. Yeah, we'll be going more into shaders. I'm pretty sure. Yeah, that's what it sounds like. So yeah, until then, yeah, I'll just see you then. Have a good one.